We're going to continue and I hope finish our discussion of the limits. So last time we defined the special kind of limits that are called equalizers. And the definition was the following. So equalizer, well, I'm going to now draw the same definition, the same diagram, but a little bit differently. I want to point out how you can generalize this to the general limits. So here, in this situation, well, you have a diagram, so something in the category, two objects and two maps in this case, but it has potential for generalization. And then over this diagram, you kind of choose an object. Say, in the case of equalizers, we call this E, right? And from this object, you just construct the maps to all the objects in the diagram, such that whenever you see a triangle, this triangle is supposed to be commutative. For example, this triangle with the F is commutative, this triangle with the G is commutative. But also you can notice, since you have this commutativity of the triangles, and say if you call this map E, well, say this map is E, right? So then the condition is that the FE is the same as the GE. In this case, so if you go like this, or you go like this, you still get the same map. So this additional information, this additional arrow that we can put in general, if you consider some diagram, it's not necessarily in this case. So we can as well just remove this, right? So if you don't have this arrow, you can immediately reconstruct this by taking any of these two compositions with E and F and E and G. But potentially, if you want to do something more general, you take a diagram, and then you construct what is called a cone over this diagram. So this, so I don't know, additional piece of information. So you have a diagram, so let me draw this separately. So this is a diagram, something that sits in the category, and over this diagram, you have a cone. And in the sense, equalizer, or limit in general, is the cone that's most, well, the cone has a vertex, which is an object, and the limit is the cone such that this is closest to this diagram, well, as possible. Meaning that whenever I have any other, I need to raise the title. So we take this category of cones, and whenever I have any other cone, meaning that you have some E prime, and then you have some map, little E prime, so again you can reconstruct the other map if you want. So there is a unique map from this new cone to the cone that you consider to be a limit, in this case equalizer. So that's again just a preparation for the general idea how we're going to define limits. So you can see that even in these special cases, it's kind of what we have, diagram plus a cone over this diagram. Then the limit is the universal cone, meaning that this is the terminal object in the category of all cones. Okay, so we have an example. I don't know, do I really need to explain this? Perhaps it was clear even from the last time. So you take the category to be the category of sets, and you want to understand the equalizers in this category. So let me use notation EQ of the F and G for the two map of sets, X and Y, as in this diagram. Then equalizer is precisely the set of points, so all the little x's in the X, such that f of the little x is the g of the little x. Sure, yeah. If you want to talk formally, the equalizer is the pair of an object and the map, right? In this case, it's very easy to see what the map is. So because equalizer, just by how it is defined, is subset in the set X. And so map little e in this case is just the embedding of one subset into another. Okay, so this is kind of natural guess, the equalizer is just this set. But is it clear that if you try to do the try to understand the universal property, that it follows from this definition in terms of the elements? Do you see it? Can you explain it? what would be the explanation? So suppose that now I have any other set right here, right? And I have another map, say E prime, to this set X. And I know that if I apply these two maps, the answer is the same. So this is also given, right? But if this is the case, right, clearly there is a map just that theoretically from this given set, E prime, to this set where the F and G are coinciding. And of course, just kind of obvious that this map is unique. It's the only thing you can do. Well, think about this, but if this is not clear, I just don't really know how to explain this with more details. It's kind of simple exercise in the set theory. Okay, so that's the one example. And I just want to briefly mention that if you consider other examples, for example, say this was example number 1 with the sets. And if you want, for example, to consider 2, say with the groups, monoids, then the same formula for the equalizer works, right? You can check that actually if you put a structure for example, group in this case, then this will be a subgroup, and this will be the embedding of subgroups. So the answer is algebraize the previous formula. And in the topological situation, again, the same formula works. So topologize the previous formula. So in this case, this will be a closed subset given by this condition. You put a topology on this closed subset, and you consider the corresponding embedding of a closed subset into the topological space. Maybe to relate with something that we already know from the elementary algebra, we can look at the category, say, of the left arm modules. And in this category, what is the equalizer of two maps? So can you guess the answer in this case? No, the objects are modules, so this is supposed to be a submodule. So in this case, X and Y are two modules. There are two maps between two modules. So there's supposed to be some submodule inside X. Well, at least, well, it's not necessarily a submodule, but it's some module with a mapping to X, but it will be a submodule. Well, what if I tell you that G is 0?
Which is maybe curl F minus G.
Yeah. So equalizer in this case is precisely the kernel of the difference. Right? Definitely this is true if G is 0, because kernel has universal property that's precisely the same as the universal property of this equalizer without any changes. But if the other map is not 0, right, so you look at the kernel of the difference, it will be some submodule. And you look at the universal property for the kernel of the difference and the universal property of the equalizer. These are again two universal properties. The kernel of the difference? There's no such thing as a difference between two maps of sets. So here we're using that if you consider, say, if you want to look at the home between two modules, again, let me call this X and Y, over the ring R, we know that this is an abelian group. So there's a meaning of the difference between two maps, because we can define difference between two elements in any abelian group. Here in this case, if you look at the home set, this is just a set. There's no difference. And your question, an answer to this question is essentially the reason why in the category theory we need equalizers. Because when you do something like linear algebra or modules over ring, we don't really need this notion, because this notion can be reduced to the notion of kernel. There is nothing really new in this notion. But when you don't have a notion of an abelian group, for example, on the Hom set, well, potentially you can consider two maps and take this kind of diagram, take the universal cone over this diagram. And as before, with the products and pullbacks, we can, sorry, pullbacks wasn't discussed yet. So with the products, you can do this for two arrows, like a binary products, but you can do for any set of arrows. It still makes sense. With the same idea, you just look at the diagram with a huge amount of arrows between two objects, and then you look at the corresponding universal cone over this diagram. Okay, so I think that basically most of the properties of these equalizers and other elementary limits are very easy to show. So I'm going to leave this as an exercise. So the claim is that whenever we have a equalizer, this map little e is always a monomorphism. So I'm continuing to use the same notation as before. And the proof is really just one diagram and one line. So I'm going to leave this as an exercise. And there is another proposition that kind of captures some elementary properties of the equalizers. And this proposition is so easy that I don't really need to prove it. Just want to state this for completeness. So the following four conditions are equivalent. So the first condition is f is equal to g in this diagram. 2, the map E is the identity. 3, map E is an isomorphism. And 4, E is an epimorphism. For the proof, I want to say that this is clear. Right? Or just what do you need to do if you want to prove this? You go in circle starting with 1. Clearly 1, if f is equal to g, well, you can take as an equalizer to be just the identity and check the universal property. Clearly it is satisfied and E is unique. So 1 implies 2. Well, clearly 2 implies 3 by trivial reasons. Clearly 3 implies 4 by trivial reasons. And now if E is an epimorphism, just using the cancellation property for the epimorphisms and that equality, f E is equal to the GE, you conclude that f is equal to G. So that's really a very simple statement, but sometimes it's useful to know when you work out with some examples or maybe proving something that these two properties are equivalent. Okay, so that's all I really want to say about equalizers. And another special kind of limits are pullbacks. So definition, again, as in any situation with a limit, we need to look at some diagram and then discuss what's the universal cone in this diagram. So in this case, the diagram is the following. So a pullback of a diagram. So now I have objects x, y, and z, and two maps, f and g, that are arranged as follows. F is from the x to the y, g is from the z to the y. So a pullback of a diagram, oh, it's again triple, formally speaking, but as with the products, usually when people talk about pullbacks, they only talk about the objects and kind of the maps are understood. So the triple where x product with z over y, that's the standard notation for this object in the category theory. And there are two projections, say pi 1, pi 2. So such that, well, usually when we talk about pullbacks, we arrange this data a little bit differently. We arrange this as a square. So we have x, which is mapped to the y, z, which is with the map g mapped to the y, and then there is pullback object with two projections, P2 and P1. So, but if we want to look at the general picture, so again, this is the diagram in the category, and this pullback with projections, is precisely the cone of this category, right? Of course, if I do this kind of generally, I'm supposed to get additional arrow to the y, but this additional arrow can be easily reconstructed as this composition through the v, or this composition through the x. So this diagram, of course, need to have a universal property. So which means that if such that how to formulate this? Okay, such that, let me say, the square is this square is commutative, and we have the following universal property. So if, say, T with two projections, T2 and T1 to the x, T2 to the z, and projections means that this is a commutative square, so kind of take the same diagram, take another cone of this diagram, so such that if there is a commutative square, then there is a unique map. Let me call this T. This is a map from the object large T to the product. Well, and of course this unique map has to be part of the diagram. So in this diagram we have the commutative square that we have in the definition. Then there is additional T that has maps T2 and T1, and then for this data there is unique T. Here, this is X. Yeah. So, and again, you can see kind of the general situation from this diagram also. This is the diagram, right? So these three objects and two maps, F and G are given. And then over this diagram, you consider this kind of category of cones, meaning that you have a vertex of this cone, and from this vertex you have a map to each of these objects in the diagram. And then among all these possible cones, you kind of find the cone that is closest to the diagram. And for the limits, it means that you look at the terminal object in the category of cones. So you can see that we can introduce the corresponding category, as we've done this in the previous examples of limits, and talk about the terminal objects in this category of cones. Yeah, I want to make a remark about terminology. So terminology, because there are so many books on the category theory and so many papers, the terminology might be different in different sources. So pullbacks are also called fibered product. And also called Cartesian squares. Cartesian squares. So these are another terminology. So fibered product I like. I can say fibered product, or I can say pullback. Cartesian squares I really don't like this terminology, because there are also co-Cartesian squares, and I always confuse what are Cartesian, what are co-Cartesian. So I prefer pullbacks and fibered products. And this is so say this is terminology. And for notation, there is also a little remark that you can notice that in fact, of course, when you write a hybrid product like this or pullback like this, it doesn't really depend on the objects x, y, and z. It also depends on the maps f and g. So it really depends on the diagram, not just objects. So for this reason, sometimes people use notation where they write product and write f and g, and in the middle and the left bottom corner and the right bottom corner of this product for the maps to indicate what maps you're using. Well, sometimes, well, it could happen that you have the same three objects but different maps and you want to consider different pullbacks, so it might be important in this case. And another notation, which not used very often, but sometimes you can see this, just use the symbol of product. Okay, so that was remark about terminology and notation, and let me also formulate this remark about the columns. So remark, a pullback is the terminal object in the category of columns. Well, I didn't use this term on the last lecture, but perhaps I should use it. So of columns, where object in this category of columns are triples. So let me use notation as before. So we have T, T1, T2, such that G, T2 is F, T1. Is that even correct? So TG, yeah, okay. Yeah, I'm going to define morphisms right now. So objects and morphisms . So for the morphisms, I'm just want to say that suppose I have, okay, let me use notation that I have in my notes. I don't think this is the best notation, but at least I won't make a mistake with this notation. So suppose I have two objects, two triples with the properties that we have. So the morphism is just a, so the morphism is a map phi from the vertex to the another vertex, in this case from P to the Q, such that phi I is equal to the Qi composition with phi, and this is for I1 and 2. Oh, as you can see, that is precisely the definition I try to formulate here, right? So the objects are these triples, the vertex and two maps, and the map between objects is precisely a map between the vertices of the triples, such that whenever we have a triangle, this triangle has to be commutative. So in this case, this triangle is commutative and this triangle is commutative, and that's expressed by that formula for I equal 1 and 2. I don't quite understand. I think that's so that's well. If you have doubts, maybe we can do this on the diagram, and then there will be no doubts. So in the diagram we have x, f, y, g, z. So suppose we have P somewhere with projections. Let's start with the Q. So here we have Q, Q1. This is Q2, this is 1, and now we have P. So this map is pi 1, so this map is phi 2, and this map is phi. So,
Okay, yeah, right.
okay, and of course we need to look at the example that we get in the category of sets. So example, so let's take the category of sets, and then so the fiber product or pullback is just all the pairs, all the elements x and y, such that f of the x is the same as the g of y. So this is all the elements in the product, just this usual Cartesian product of two sets on so this is a product. This is x, y. Ah, okay. Okay. That's the definition. That's the definition. Well, in this remark, what I'm just stating the definition one more time using this additional category of cones. You can do this directly just by looking at this definition, right? What I claim is that for any triple with a T, there's a unique map like this. But that's exactly meaning that this triple, which is the fiber product, is the terminal object in the category of such triples. Okay. So let's look at the one special case. Again, the logic of this example is more or less as the logic with the equalizers. So I'll leave this as an exercise to check that this is indeed the pullback in the category of sets. But you know several special cases of this construction, probably from the school, if not from the school, from the first year. So what if I consider the following? I take just an element, little x, and consider my first map, which I called f before, just to be an embedding of this element in the x. And the second map is just something, y. Or maybe let's change notation a little bit, let's call this map f. So in this case, what is the pullback? Yeah, that's a fiber over x, yes. Well, as I mentioned, the notion really depends not on the objects, but on the maps. So we have f and g here. So this f and g have the target. The target is y in this case. Wait, well, it looks like I changed notation. Well, I changed a little bit notation. So before it was the target was y, but in this example, turns out that the target is z. Like the same thing. Okay, so in this example, the pullback is just the fiber of this map f over this given point. And this is for a reason why, if you do something like algebraic geometry, it's unavoidable to do pullbacks, right? You define the category, say, of some algebraic things that you want to call spaces, like schemes, or algebraic spaces, or stacks, and then at least what you want is to look at the fibers of some maps. And if you want to look at the fibers, well, you need to consider diagrams like this, which are pullback diagrams. And another kind of explanation why we want to call them pullback, well, in this case, well, you have this map in this case between sets, right? And you kind of want to take this map and pull it back along this map in the diagram. So in this case, if you just, it's just embedding of the point, you pull it back under this map, you just get the fiber which is mapped to this point. Another special case that you definitely know is the following. So suppose we have two subsets, X, which is embedded, say, into Z, and Y, which is another subset embedded into Z. So these two maps are two embedding of sets. What's the pullback in this case?
Intersection of images.
No, just intersection of two subsets, since we consider them as a subsets. So in this case, the pullback is the intersection. Well, since this is just a fiber, and the fiber is by definition, well, what would be the standard definition set theoretically? The fiber over a point is just all little y in the y, such that f of y is equal to this x. So by the definition, this is subset in the y. And so this map is just the embedding of the subset, inclusion of the subset. Okay. And you can use now this as a motivation to give a definition of an intersection of two objects in a category. Suppose you have some abstract category. You have a situation where you have object and two monomorphisms. You want to call such pairs, say object plus monomorphism, as a sub-object. And you want to define notion of intersection of two sub-objects. Well, suppose you know that in your category you have pullbacks. Well, then you can take this just as a definition. And again, I want to emphasize it's not immediately clear if you work with some new category that this category has pullbacks. It's possible that in some categories that you might be interested, there are no pullbacks. Again, and as for the equalizers, there are several elementary observations about pullbacks. So the first one, and I think I want to leave almost all of them except one as an exercise. So pullback of a mono is mono. Well, in more details, it means the following. You have the pullback diagram with the x, z, and y with maps f and g. Two projections. So the statement here is that G is mono implies that the projection P1 is mono. For shortness in words, we just say pullback of a mono is mono. Just a general categorical property. So essentially all you need is just to combine two definitions of a pullback and monomorphism. So the proof will be exercise for the seminar. Yeah, because this everything is completely symmetric, we can do this for the f and p2. Yeah, it's automatically. So the second proposition, which is maybe even easier to show. So again, exercise. So a map or an arrow in a category f from the object x to the object y is mono if and only if the following diagram is a pullback diagram. So on the top I have identity mapping x to the x. On the bottom I have f mapping x to the y. And then the left vertical arrow is identity on the x and the right vertical arrow is f. So if and only if the square is pullback. So proof of this thing is left as an exercise. But the next proposition I want to prove, I think is a little bit more interesting. No, proposition. If a category has binary products and equalizers, then it has pullbacks. So this is the first proposition showing that different kind of limits are not independent. If you have some special kind of limits, you can express other limit using this special kind of limits. That's a general phenomena that we're going to discuss later. Okay, so to prove this, you really just need to look at one diagram. So I want to show that there are pullbacks. So let me start with a diagram for the pullback. So I have X, F, Z, Y, and the map G. Well, I know that I have products, so I can form a product of the X and Y. So let's take a product of X and Y, call the projections pi1 and pi2. Right, so, and then we look at the equalizer. So let's say E pair with the map little e is the equalizer for the following maps. So F composition with the pi1 and G composition with pi2. Right, so there are two maps from the product to the Z. They are the same by the constructions. This is just a product. So there is also somewhere object E, which is the equalizer, and then for this object E I can define two projections. So I can say that there is projection P1 and I can say that there is a projection P2, which are by definition are the following. So here also there is map little e. So P1 is defined as the composition of the projection pi1 in E, and P2 is defined as the composition of pi2 in E. Okay, so I claim that the object E that I constructed here by taking first product and then the equalizer is in fact the pullback. So we want to show that E is in fact isomorphic to the fiber product of pullback. Okay, so to do this, let's suppose that I have another diagram. So I have some T with maps T1, T2. So there is a question how I can construct a unique map U that lives here. Okay, so let's do a little computation. We know that F1 composed with T1 is the same as the G with the composition with T2. Let's rewrite this a little bit. We can say that the F we take composition with pi1 and then T1 and T2 in angled brackets, which is tautologically, so this composition of these two maps is the same as T1. Right, so then this is equal to the G pi2 T1 T2. Okay, now using that we have equalizers, I can say that there is a unique map U from the T to the E such that E is precisely this map T1 T2. Right? So for this implication, I'm using that I have an equalizer.
May I ask if you remind what does the triangle vectors mean?
Well, that's a map that you get if you have a product, right? And how you define a map to the product. It is enough to define the map to the components of this product. In this case, this is T1 for the first component and T2 to the second component. Then there is a unique map from this object, to this product, and the notation for this map is precisely this T1, T2 with the components. Okay. So it's essentially what we can derive by looking at this diagram and this computation is that if I look at the category of cones, where I first consider cones where I take equalizers, so for the maps F composed with P1, and G composed with P2. So this is to the Z. So such category of cones is the same as the category of cones for the original diagram. So if you have cone over one diagram, you can construct cone over the other diagram, like we've done here, and using the same logic, we can construct cone in the other direction. So the category of cones are equivalent, in fact. So that's an equivalence of categories. And since the categories are equivalent, well, the terminal objects exist at the same time. So here the terminal object is the equalizer E. On the right-hand side, the terminal object is the pullback. So they have to be isomorphic. So this is one proposition that I want to show, and there is one more, much more elementary. So a category has finite products and equalizers if and only if it has pullbacks and terminal object. The proof is exercise. It's another example where you can reduce one kind of limits to another kind of limits. Okay, so finally, I want to give a general definition of a limit. So let's call this limits of functors and functors means that we consider diagrams. So definition, a limit of a functor, so let's call this functor D. D stands for a diagram, so from some small category I, well, in the definition it's not necessary to assume that I is small, but usually it will be small, because if you require something like you have all the limits for not necessarily small categories, it means that your category C is actually quite elementary. So here, before I continue the definition, I want to immediately discuss how we're supposed to think about this functor D. Well, it means that we have some sort of diagram in the category. So we have a bunch of objects. Something like this, n maps. And this diagram, if you think about this abstractly, you can think about this as a category. I call this category I. So in the category I have objects that are well, just copies of the objects in the diagram, and for each map in the diagram, I have the corresponding map in the category I. So, for example, what category I is supposed to take if I just take a product of objects? Say it's just a set of objects, and I want to formulate this diagram that I have a set of objects using this functor, D. Do you understand the question?
No.
Well, I want to think about such functors from some category I to the C as diagrams inside the category. For an example, such diagram will be diagram for the product, which is just a bunch of objects, and there are no arrows between those objects. What the category I is supposed to take to represent this bunch of objects by a diagram, which is a functor. Okay, take two objects. Well, then the category, yeah, then the category is just a set with two objects. If you have a set of objects, then the category I is just the set.
We should take some categories.
Hmm?
We should take some subcategory maybe.
Subcategory of what?
Что?
Subcategory of what?
C.
No, C is given. Now, what if I take, for example, I to be equal to the following category? Well, just two objects. I don't want to write the identities. Identities are always there, but there are no other arrows other than identities and just two objects, right? And I look at the functor from this category to the C. It precisely means that I choose two objects in the C. So in this case, the examples that we discussed before, the binary products, the equalizers, this is the diagram, or the pullbacks. Sorry, pullbacks is it's another. Yeah, so the pullbacks are just these three objects and two arrows. So if you consider I as in these three examples, you get the diagrams precisely as for the binary products, binary equalizers, and pullbacks of two arrows. But you can do this quite generally. You can take any diagram that you want. Well, I try to draw an example here, much more complicated diagram. And you can talk about the limit of such diagram or limit of a functor. So the limit of a functor, limit of a diagram is a terminal object in the following comma category. So delta D. So meaning that we consider category C, we consider the constant functor from the category C to the category of all functors from the I to the C, and then we also consider the functor D lower star from the category with one object. So you form the corresponding comma category, you take terminal object in this comma category, and this is by definition called the limit of a functor. That's a nice, very short definition. The problem with this definition, you can't understand anything that's going on in this definition, just a bunch of words. So let's think about this a little bit differently, what this information represents. So the object in such comma category is supposed to be a map from the constant functor. So in this case, delta is constant functor. So from the constant functor we have a map, natural transformation if you say so, P to the given functor D, which is supposed to represent a diagram. Well, since this is a constant thing and this is a natural transformation, this information is equivalent to information that I have a vertex C, then for any objects d of I and d of j, so in this case I have map u from I to the j, and this is supposed to be, of course, or in other words, u is in the I, little j. So then I have projections Pi, then I have projection Pj, and such square is commutative. So as you can see, if you want to represent this graphically, this is precisely what I called a cone earlier. So this information here, I'll say just this part of the information, is I have a vertex C, and then I have projection to each of the objects that I have in the diagram, and whenever I see a square, whenever I see a triangle here, this triangle is supposed to be commutative. These are all such triangles. This is for any I, j, and u.
May I ask, C is an object in I or where?
C is object in the category C.
But I can understand how we obtain a functor because triangle is triangle with sub C should be a functor from I to C.
Yeah.
Right?
That's the constant functor. It takes any object in the I. So if you look at this functor, triangle sub C, apply this to some vertex, which is an object in the I. So this is supposed to be just C. So it kind of the map between two diagrams, but this diagram is just one vertex and no other information. Okay, so if you understand this formal definition, it's fine. It's a very short way to formulate this. But really what is hidden behind this definition is just that we take a diagram inside a category. We kind of think about this as a functor D from some category I to the C. Over this diagram, we can consider cones like this. And in this category of cones, we have terminal objects. And the terminal objects are precisely the limits, right? Because if you have any other C prime such that you have all these maps, well, it's going to be messy now. So then there is a unique map from this C prime to C. Okay, I have again a couple of remarks. So first remark about notation, terminology. Again, the reason is that there are so many different texts, especially old texts, that... Wait a second. Yeah, so maybe somewhere in the definition I also need to give this thing a name. So the name is limit over category I of the diagram D. So this universal cone, the terminal object in the category of cones, the vertex has name limit I D. And of course, the same as with other examples of the limits, well, formally speaking, the limit is not just this vertex. The limit is just this vertex, is the vertex with all the projections. So if you want some more precise notation or terminology, so the limit is this object plus all the projections by I, and this is for any little I in the as an object in the category I. Well, this thing takes an object here and sends this object to a constant functor, which is this functor with this definition. Yeah, so back to the terminology. So this limit, sometimes people use other notation with the arrow going like this and call this inverse or projective limit.
What is the right part of the diagram with D substar? What is the domain of D substar? Just one?
Yeah, so this is just a category with only one object.
Okay.
And we discussed this earlier. When we take a category, take an object in this category, and we can think about this object as a map, as a functor from a category with one object to this category. This is the same thing here, except this category in the center is a little bit more complicated. There's a category of functors. So to fix an object here, I need to fix a functor, which is precisely what I have. Yeah, so this limit sometimes is also called inverse or even projective limit. But I think this is kind of old terminology, and I'm going to reserve this name of inverse and projective limit for very special kind of limits that we're going to discuss after we finish this general nonsense. And another remark which can relate the limits and the adjoint functors is the following. So let alpha from D to E be a natural transformation of functors. So I assume that I have kind of two diagrams of the same shape and the natural transformation between those diagrams. So then using that the limit is the terminal object, I can notice the following. So the constant functor of the limit D has map P to the D. So here we have natural transformation to the E. So here, and also when the diagram is kind of understood and there is no place to write this I, I'm going to write just limit D, limit E. So I is kind of a little bit abusing notation. So then there is a unique map like this, and we can call this map limit of a natural transformation, and we can conclude that the limit, okay, maybe I need to write I here because I want to use it later. So the limit sum I so is a functor, and moreover, if you look at the category of functors from I to C between the constant functor and some functor D, this is the same thing as the home in the category C from the object C to the limit of D. So this natural bijection follows immediately more or less from the definition of limit as a universal cone. And the conclusion is that the limit sub I is in fact the right adjoint functor for the triangle functor. So if you wish, that's another definition of a limit, but I'm pretty sure that it's not possible to understand this if you don't know another definition in terms of cones. So later we're going to discuss colimits, and the colimits will be the left adjoint functors for this triangle or delta. Okay, so now we have one important theorem. So if category C has binary, I'm just saying binary for completeness, equalizers, and products indexed by objects of I and the arrows of I, then there is a limit for any diagram over I. So there is limit for any d I to C. Right, so it's a very surprising theorem if you haven't heard about this thing before, because here I can take any diagram that I want, and the claim is I can reduce this diagram to just two kinds of diagrams, products and binary equalizers, and that's enough. Это все стрелки. Okay. So for the proof, we can look at the following diagram. So suppose I have some object T with the map little t to the diagram where I take a product of all objects d of I, where I is in the I0. Well, for shortness, I want to say that I0 is by definition this set of all objects, just to have some short annotation for this product. So that's the product. Then I consider maps phi and psi to the product over all arrows in the category I from the object little I to the object little j, and then I take d of j. So that's the diagram I want to study. So in this diagram, well, first of all, I want to mention that product is taken over arrows, but this is still product of objects. This is g of j, not g of u. It's kind of important to emphasize this from the very beginning. Now I want to define these two maps, phi and psi, right? Since I take the maps to the product, I can completely understand these maps if I understand the composition of these two maps with the projections. So here, for this product, there are projections pi to the d of I, and here there are projections that I can call pu to the d of j. Okay. So let me say that by definition I want composition of the projection pu with the map phi to be the same thing as the projection pj. And I want composition of projection pu with the map psi to be composition of the d of u with pi. So let me just maybe write this in words because it's important. So these formulas define maps phi and psi. Okay? Что? Это отображение в категории I. Well, it's what it is here. Right, so this is the reason why I need the product to exist over the objects, because I need this product to exist, and I also need this product to exist. And existence of these two products is the assumption of the theorem. Now I'm introducing two maps. For these two maps, I can take equalizer, and of course the claim is that if I take the equalizer, this will be precisely the limit of the functor d that we have. I don't understand this objection. So I have they said that parameterizes product is a set of such maps. I take an element in the set, this is u, and because it's a product, I have a projection. It's not just part of the definition of a product. And this is projection to the d of j. Yeah, so since we have a map to the product, and a map to the product is completely determined by its components. So I'm giving you the components, and if I'm giving you the components, I'm precisely give you the maps. Okay, so these are definitions of phi and psi. Now let's look at the condition that the composition of the phi t is equal to the composition of the psi and t. Right, so I'm now essentially I'm looking at the corresponding cones. So this means, oh, okay, I can, if these maps are the same, the compositions with the projections are the same. Right, so I can add an additional projection PU. Now I can plug in my definitions and say that the P sub JT is equal to the D of U P sub I T. Right? Now well, this is the same thing by saying that the T with the index J is the same as the D of U T with the index I. Where I just use these compositions as the maps Tj and Ti. But this last condition is precisely the condition that a triangle is commutative. So this is the condition that the object T together with the maps Ti that I just introduced. Oh, this is, say this is Tj, this is Ti. Together with all these maps, so this is a cone over the diagram D or over the functor D. So we can see that information that we have a cone over D is precisely the same information as we have map little t to this T, to the object T, to this product, satisfying this condition. This is just the same two sets of data. But it means, as before, the logic is the same. It means that the category of cones are equivalent by this bijection. And if the categories are equivalent, they have isomorphic terminal objects. And the terminal object in one case is this limit, and the terminal object in the other case is the equalizer of this diagram. So hence, this is the end of the proof. Okay, so since this is one important theorem, maybe I can pause for a minute and try to answer your questions. Do you have any questions about the proof? Well, what exactly do you want me to draw? Well, the logic is the following. We look at this diagram. So at the moment, I don't assume this is equalized. I just look at any diagram with any large t and little t. Okay. So in this diagram, I can, well, first of all, I define these maps phi and psi using this definition. So essentially, these two lines. Is it clear so far? That this actually defines two maps. Yeah, so and then I have just this little computation. Well, on one hand, I have condition that this is a cone for the equalizers, meaning that I have this condition, right? And the category of cones of the equalizers have this condition. Then I do computations step by step, and I think this is really very simple computations. And at the end, I'll get the result that I can look at this T composed with all the projections, and this precisely give me a cone over the diagram that I given in the theorem. So all these things are equivalences, and I think it's pretty much easy to see that every equivalence is true by tautological reasons. If I have this equality, this happens if and only if the composition with the projections holds, right? So here, here the only thing I do is just plug in the definitions, all right? So we just introduce new notation, rewrite the same identity, which tells me that this is the condition that all the correspond. Well, if you want a diagram, maybe the only diagram I can draw is the T. So here, say this is diagram. So this is Ti, this is Tj. Let's say this is I, this is J, this is U. So this formula means that the corresponding triangle for this particular U is commutative. Well, I could potentially have some u prime, I have another condition for u prime, etc. And all these conditions together are precisely conditions that this is a cone. Yeah, but the limit is t if you think about this as an equalizer for this pair of maps. Yeah, so I can write this formula. So the limit id is equal to the equalizer of the phi and psi. Okay. So now I have just one more kind of limits that I want to discuss because they're still important. And I'm going to call this inverse or projective limits. So these are limits over directed sets. So definition, a directed set is a set with binary relation that I'm going to go less or equal such that it satisfies three axioms. So first, the trivial one, I is not empty. Two, this relation is reflexive and transitive. And three, for any I and j in the set I, we can find k in the set I such that I is less or equal than k and j is less or equal than k. A typical example of this situation is natural numbers with the standard less or equal relation.
What is reflexive?
Reflexive and transitive. In all examples that I'm going to say that I have ordered set, you can think about this n. It may be useful. So of course, I can think about this directed set as a category. Right? So the objects are elements of this set, and if I is less or equal than j, then I have a map from I to j. Well, this is the condition for any two pair of objects. You can find another object. Well, you have I and j, and you can choose a third object so that I is mapped to k and j is mapped to k. Okay, so it looks like I don't have a lot of time to do this, but I'll give you one more definition. An inverse also called projective system in C is just a functor D from the opposite category of I to the C, where I is directed. So in this case, the corresponding limit of such diagram is called projective or inverse. So projective or inverse limits are just very special kinds of general limits where you have additional requirements on the diagram. So the diagram has to be just a directed set. So this is kind of part of a general theory, but you can do this directly. You can say the following. So an inverse system is just a bunch of objects parameterized by some directed set I, and the maps Fij from the dj to the di for any I less or equal than j, such that we have two conditions. So first, Fii is the identity on the di, and two, since this is a functor, it maps compositions to the compositions. Fik is equal to the Fj composition with Fjk for any I which is less or equal than j and j less or equal than k. So sometimes in the literature, when people don't want to work out the general theory of limits, they just give this as a definition of an inverse system, and then there's a definition of the corresponding inverse limit. Okay, unfortunately, we don't have time, but next time we're going to start with one interesting example of such inverse limits from the algebra called completions of modules or rings. So let's take a break. Нет, давайте вопросы после. So 2 weeks ago there was a problem that we started but never finished. So let's finish this today. So in this problem I have a forgetful functor u from the category of pointed rings to the category of rings. That just forgets the distinguished object. And the question was to find, well, describe it if it exists, or show if it doesn't exist, the left adjoint functor for the u. No, it's close, but not exactly. Okay.
What about this problem? So we need to construct a functor from rings, pointed rings, right? And I want to do the following. I want to take a ring R and I'll have I have this ring, right? And I want this variable t to be the point element.
Well, what kind of polynomials you consider? Because the ring is ring R is not commutative.
So we don't have.
So what do you want? If I write something like AT, is this the same thing as DA or not?
Well, it shouldn't be actually. I don't think it should be this way.
Yeah, so he wants this kind of non-commutative polynomials, right?
Yeah,
Yeah.
F's in common. Yes.
Okay.
So now I'm to prove that it is adjoint to U, right? So I want to say that if you allow me, I'll use your intuition. This is what I need to do. I'm not. It should be the contrary. Okay. Well, one direction is clear, right? I mean, this ring contains this ring is a subring, therefore I could just use the restriction, and if I have a homomorphism of pointed rings here, I could just restrict it in the ring R and we are good, right? Vice versa. Assume we have homomorphisms of just rings psi, and I want to construct a homomorphism of pointed rings. Well, by definition, actually by the very definition, by the universal property of this object, there is a unique homomorphism of rings from RT to S, such that T is mapped to the pointed element of S. So I said psi tilde, and psi tilde, and I say that there is a unique psi tilde such that psi tilde of t is a point, and psi restricted to r, psi tilde restricted to r is just psi. Right? It is more or less the definition of the polynomial ring. And well, clearly it is a projection, and it is clear that it is factorial. Therefore, we're done.
Well, all these things you really need to check, and you need to keep in mind that if you want to, on a solution, you need to check these things. But usually, when you have maps in one direction, the other direction, the rest is quite clear. So usually we don't do this even on the seminar.
Very good then.
Okay, if you don't have any questions, then that's it. Don't forget to write the name.
Естественность очистится.
Ну, я могу проверить. Вообще, я слышу,
Ну, у нас есть отображение удостоверно, проверить, что это делается.
я слышу, обычно люди, чтобы доказать, что это функтор, они делают по-другому. Они берут, например, вот это вот про универсальные стрелки как раз. Они последовательно два функтора и проверяют, что в обе стороны все пропускается, даже в одну хватает. Понятно, что я имею в виду, или не очень понятно?
Ну, так тоже можно сделать, но
Да.
если вы сделаете просто напрямую, проверите, тоже сработает. И я даже не уверен, что в итоге будет как-то сильно проще или короче.
А что вы имеете в виду напрямую? Ну, возможно, это же есть напрямую.
Нет, но здесь же надо еще проверить, что это не просто BX, да?
Нет, я имею в виду, что потом было сказано. Понятно, что надо не только BX проверять, а что это изоморфизм функтор.
Нет, я имею в виду, что просто вот напишу по-честному, там пусть у нас есть одно кольцо, другое кольцо, между ними есть отображение. И просто убедимся, что ну, здесь как бы аргумент такой, что как бы у вас конструкции естественные, ничего не зависящие. Но здесь шанс на то, что они функциональные, очень хорошие. Соответственно, теперь можно, если захотите, просто брать и проверять. Просто если бы там, ну, не знаю, действительно что-то зависело от каких-то выборов, то, скорее всего, шансов бы не было никаких.
Хорошо, а вот на контрольной, допустим, вы хотите, чтобы мы проверяли что-то?
Нет.
Okay, so one more problem. Now functor U is a functor from the category of all not necessarily commutative rings to the category of monoids. And this functor is taking a ring and sends this ring to the monoid with respect to the product. I'm not sure what would be the best notation, so this is my notation. So you take all the elements in the R, you forget about the addition, and you use only multiplication. Under multiplication, this is a monoid. So you can associate two monoids to the ring under addition and under multiplication. In this case, I want under multiplication.
The same question. Find vector joint or explain why it doesn't exist.
Well, it's not clear that it is like usually. It could formulate some sort of general theorem that if you have sort of free objects in the category, then always have sort of this sort of adjoint.
Ну, в смысле, надо еще доказать, что он существует.
Ну, на всякий тоже имеет такое представление. Нет?
I don't quite understand what you're even saying. So, yeah, sure, we have three objects in the noise, but three objects in the ring, then what?
Again, I try to give a solution.
Well, give an answer. First of all.
Hmm?
What's the answer?
I do it, yes. So
That there is no? No. There is a vector joint functor.
I do it, yes. And I do that by the standard construction of a car presentation of an object.
Okay, if you want to say something, maybe you do this on the whiteboard, it will be easier.
so I want sort of the closest ring to what I get, what I have. What do I want to take? I think on something like the following. So, we could construct sort of a free ring on a given set, right? That's what I mean. And I want to impose the following relations. I want that okay, let me distinct two different multiplications. I say that monoid has the multiplication dot, and my ring will have the multiplication star. Okay? And I want the relation that x star y equals x dot y for any x and y from my monoid. So that's a well-defined ring, right?
Yeah.
And quite possibly this will be the joint functor we're seeking.
Well, this is a functor definitely.
Okay. So then I need to show that they are adjoint. The main thing is not to screw up left and right here. So I want to construct a bijection, right?
Is it you or
You. So what can I say? I mean that, well, it is a ring and it is also a monoid. So we naturally have the inclusion of monoids. So like this huge. So and given the homomorphism of rings, I get homomorphism of monoids by postcomposition. Right?
okay?
And vice versa, given a homomorphism of monoids, I get the homomorphism of rings, because by the definition of co-representation, this sort of the initial object, it satisfies these conditions, right?
I'm not sure about this. Well, you can do this if you know that this f of m is a free ring on a set, right? But this is not a free ring.
Yeah, I mean, okay, then it's sort of the isomorphism theory. I have the Turing ring on the M, and I try to explain it in words, but I cannot see it. So
I
we
think,
have.
I think it will be better if you just write it from the very beginning.
Okay, so
Maybe you can erase on that little blackboard and to use it.
okay, say that. How should I write the free monoid name? Okay,
Maybe T of m.
Okay,
Not sure.
T of M, T of S, free ring on the set S. Okay, what do I have? Given psi, I have the set M mapped to R. Therefore, we have T of M mapped to R by the very definition of T of M.
M map to, oh, the m map to r is, this is psi exactly, right?
Yeah. Okay. Now, what is f of m? F of m is TFM quotient by the ideal generated by these relations, right?
Mm-hmm.
So we have this projection here, and the question is whether this the upper arrow factors through this projection. Well, the isomorphism theory tells us that factors if and only if these relations are satisfied in R, right?
Mm-hmm.
And they are satisfied because psi is a homomorphism of monoids. Therefore, we get unique factorization, which is exactly, precisely such a.
No, there is a mistake somewhere. I know this is not the right answer.
Probably I have an answer.
No.
I think it should exist, and we can use something like polynomials, короче, полиномно z с переменными моноида, z and n.
Mm-hmm. Yeah, I think that's the answer I like, but maybe we can also try to find a mistake.
Is it different from what I'm giving?
Ну, в смысле, это все равно свободный объект.
Да, это одно и то же.
Нет. Насколько я понял, ответ был такой, что это что-то типа групповой алгебры.
Что?
Что типа что-то ну, моноидальная алгебра.
Там или у меня?
Там. А у
Ну,
вас,
а что у меня?
а у вас, насколько я все-таки могу судить, я просто не вижу, где есть кода ошибка.
Что такое свободный объект на множестве в кольцах?
Чего?
Что такое? Вот это такое? Это многочлены с переменными индексированными элементами множества, не правда ли?
Да.
Ну, это правда.
Ну, сделать, добавить, сделать это моноидально, надо добавить соотношение, которое есть в моноиде. Ровно то, что я пишу.
Сейчас, да, может, я не знаю, что вы пишете.
Вот я говорю, у меня есть звездочка, это умножение в кольце, которое я строю, а есть точечка, это умножение в...
Нет, ответ, который должен получиться, это, хотите мне сказать? Это вот это. Именно это я называю моноидальной алгеброй. То есть
Да.
если бы я была группой, это была бы групповая алгебра.
Ну хорошо, я пишу что? Я пишу, давайте возьмем свободное кольцо на элемент по всех элементах моноида
Да.
и добавим эти соотношения. В точности получается такой объект.
По-моему, Андрей, так и есть, да?
Просто написать так, это как бы, пока мы это не определили,
Надо осознать, я никогда в жизни про это так не думал.
просто, как бы если мы ничего не определили, то как бы это по определению есть распоряженный функтор просто. Ведь.
Не, ну, z все
Не, ну, знаете, сейчас.
Особенно, когда вот это вот писал уже, вот так, если я прям честно объясню, что я имею в виду под этим, то...
Это похоже на правду. Ну, и там у вас что получилось? Просто такие линейные комбинации, где у вас, грубо говоря...
Ну, только линейно, там еще могут быть сложнее, конечно.
Нет, линейные комбинации таких мономчиков, а мономчики и там у вас какие одинаковые, да? То есть это произведение элементов из одного.
Не, ну это же буквально одно и то же. Мы берем все элементы из моноида, берем буквально свободное кольцо, то есть буквально многочлен с формальными элементами из моноида. А потом еще их факторизуем по нужным соотношениям, чтобы, собственно, структура умножения была такая, как надо. Ну это буквально то же самое.
Ну да.
Ну, просто этот объект как бы, тоже нужно определить. Когда вы будете определять монетарную алгебру. Вот так.
Ну нет, определение такое, как вы изучали, там 30-местной теории представления, вы просто забывают, что есть обратные элементы. Мы пишем групповую алгебру, но не более кольцо, но просто формальные линейные комбинации элементов из моноида.
Их произведение. Ну, то есть, мне кажется, это будет...
Нет, ну их произведение это тоже будет как бы формальные линейные комбинации.
Да, это правда.
Нет, ну это действительно выглядит как одно и то же, да. Просто я, ну, видимо, я никогда для группового этого кольца не пытался написать по представлению, но похоже, что это оно и есть, да.
Не, ну даже в первом примере, когда мы брали, мы на самом деле брали свободное кольцо на кольце плюс точка. Ну это то же самое на самом деле, когда вот в том примере.
Да, они все выглядят очень похожи, на самом деле. Да, как будто всегда, когда есть такое представление, есть сопряженное.
Ну если у тебя есть левый сопряженный с забывающим, по-моему, это всегда свободный объект исполнения.
Я даже когда-то такое слышал от таких категорщиков, но не умеет формулировать.
Нет, ну это правда, что сопряженную функцию к забывающему функцию левый сопряженный это свободный объект. Просто это вопрос в том, как, ну, как это понять конкретно.
Да.
Да. Ну хорошо, нет, да, я думаю, что это одна и та же алгебра, на самом деле, да. Просто написано как волшебное представление. И это тогда правильный ответ. Это я сразу не распознал. Okay. Maybe we do one more example about adjoint functors. This probably will be the last one. So in this case, let's take Pareto functor from the category of topology to spaces to the category of just sets, forgetting the topology. And question is, do we have left or right adjoint, or do we have both? Or maybe we don't have left right adjoint at all. Maybe someone else can do this example.
Я могу.
So I think we need to begin as left adjoint. Okay, so if we have morphisms on
Maybe you first want to write definition of what is f of x.
yes, in this way I think it's x with discrete topology or so we wanna always any map from this be continuous, so it should be maybe anti-discrete. Вроде антидискрет, но сейчас. Because so if we have map on sets x to Как Y по-английски произносится? Y. X to Y. So we have some map from X to Y. No, well, I with no topology. So it's any map from X like a set to Y like a set. When we can just take with map with map and any fiber of open set in Y will be, oh, it's a dice cut. Okay. Any fiber of a set of open, like we take all subsets, like dice cut topology.
This is true.
Yes, this is true. So we take precisely.
The better notation for this would be something like you write X and write discrete as an index.
Okay, and so if we have an open set in Y, we take it fiber, and it is subset and effort. Ну, а fiber это слово, ну и чё, да, я не умею говорить. Ну, pre-image, and it is subset in X, and all subsets are open. So it is open.
Yeah, so essentially we're trying to solve a very simple topological problem. What topology are we supposed to put on X in such a way that all the maps from X to the Y are actually continuous maps?
So we have done with a case.
So left adjoint is just topological.
Okay, and now
Subset with discrete topologies.
our way.
I think it will be better just to raise the solution of the previous problem and start on the top.
So we have now we wanna, if we have map from X with no topology to Y, we wanna to this map be continuous. So we get yes. I think it is anti-dice cut topology. Yes, but why? And if we take some pre-image, yeah, if we take some pre-image of open subset, it should be open. But what is open subsets it in Y with anti-dice cut topology? It is empty set. It is clear what it goes to empty set. And we have whole Y, but it goes to X and it is open. Ну, в смысле, мы берем буквально тоже отображение. Ну, биекция такая, мы вот такое переводим в такое. Ну, F в F. Ну, можно это написать. Но я хочу обосновать, почему оно будет непрерывным. Оно непрерывным, потому что тут нет открытых подножеств практически.
Ощущение, что я переход
Что?
Можно писать было там fiat f, у нас было fiat.
Ну, fiat f равно фи у нас получается. Ну, в этом смысле. Ну, да, тут все хорошо, потому что тут all open subsets where preimages of all open subsets are open. So with this continuous map.
Okay, questions? Seems like there are no questions. Put a check mark. And I actually think I want to do one more problem. Of the first concept before we go to the limits.
So the problem is the following. Now this will be just two functors between the category of sets. So I'm going to call this L, since this will be the left adjoint. And L is defined the following way. So we fix set Y, just an object in the category of sets, and L of X is defined as the Cartesian product of Y and the X. So the question is to find the right adjoint for this functor.
Нет, там имелось в виду, что мы берем дискретную топологию, то есть в качестве топологии берутся все подмножества, 21х. Я тоже не сразу понял, что это будет тогда.
А мы доказание, мы это только про одну сторону сказали. Ну, с одной стороны, adjoint фактор нашли.
Нет, с собой. Но слева левый сопряженный оказался множество с дискретной топологией, а правый сопряженный оказалось множество с антидискретной топологией.
Okay, we need such isomorphism between product of two sets, and here we have maps between x and some functor from z. Okay, let's put our functor equals to z powered y, which means maps. Okay, it maps between. Okay, I will write like this.
I think it's the other way around. This is from y to z.
Oh, okay, yeah. Yeah, so all homes in sets. Okay, and so how can we construct this bijection? So suppose we have f here, so it maps from pair to element z, and we need to construct a map between x and home from y to z. So we have, yeah. So it will map to phi x. Yeah, okay, phi of x, which so give me 1 second. Так, нам нужно по элементу x получить штуку, соответственно, это как бы... Ой. So, yeah, if we have...
So it's a very simple idea. You have a function of two variables, right?
Yeah.
And then what you do, you just fix the first variable. And
Yeah.
consider this is a function of the second variable. This
Yeah,
is the
exactly.
direction.
Yeah, so, and in the another direction, if we have, so, no, it works the same way. I mean, if we...
This is not the correct notation for this situation. It's like this and like this.
Okay. Yeah, if we have map from x to morphisms between y and z, so phi, let us put f like this. So it's element in z, and so it's clear to check that it's bijection and functorial and a lot of stuff.
Yeah, so you can also compare this pair of joint functors with the pair of joint functors for the home and tensor. Home and tensor is kind of the same kind of examples and the same kind of formulas, but with additional algebraic structure. Here, this is just most parameters set theory. Okay. And so I want to do about the adjoint functors, but I'm going to update this problem sheet on the Google classes, so I'm going to add during next week more problems about adjoint functors, so I can practice on those problems, and also I might use these problems on the second quiz or midterm. So now let's do several problems about the limits. So this will be essentially statements that I left as an exercises on the lecture.
просто множество.
Доказывается точно так же.
Да, ну там было не только индуцированное представление, там была общая ситуация. Когда у нас просто есть бимодуль между двумя кольцами. So the first problem is to show that we have the following relations. So suppose f is a map from the x to the y, and there is map g from the x to the y prime, and I want you to show that the product, so this f and g, I don't know how to say this correctly. On the right hand side we have a product and the composition with the diagonal map on the x. On the left hand side we have just this map. Maybe I can write this. So we have y, product with y prime. We have projections to the y and to the y prime. Here there is x, this is map f, this is map g. So here there is a unique map, which is usually the standard notation for this map is f and g in brackets.
Предыдущего вы записали свою
Да,
фамилию?
да, да.
А вы уже уходили разве?
Да.
Я просто пытаюсь еще запомнить, как вас зовут, а как вас зовут?
Филипп Иван.
А, да.
I think I draw a diagram.
Микрофон.
Okay, I will draw a diagram firstly for the diagonal map. I think it should look something like this. And
Yeah, except x and the delta is supposed to be an index.
Yeah. And then the diagonal for the multiplication. Yeah, and from this diagram and this diagram, we'll obtain this equality, I think, because here we have composition F and identity and G and identity, so this composition will be the same as this composition.
Yeah, because there's only one such graph.
Yeah.
So next problem is to show that E is mono for any mapping of one equalizer. все, кто захотят, могут выходить достаточно быстро с доски и получить достаточное количество галочек. То есть у нас не возникнет никаких проблем.
Да, у нас микрофон. Нужно на английском, правильно? I could do this. So, we need to show that if I have two morphisms f and g, and if there is their equalizer, then it is a mono. Meaning that it is cancelable on the needed side. So, how do we show this? Assume that there is some object z and two morphisms with the target e, say alpha and beta, and we want to show that if e is cancelable on the right.
I think you need to write a little bit larger. It's very
Okay, I'm sorry.
And
Yeah.
the cameras also will be big.
Okay, so we want to show that if e composed with alpha is equals e composed with beta.
Now you think again. It's a very small point.
Okay. Hope that's visible. Okay, so if I have this, then clearly we have that f composed with e composed with alpha equals g composed with e composed with alpha, and the same goes with with beta. Yeah. Okay, I guess you still can see this. Okay, so these are all the same morphisms. I could, by the very definition, so we have this composition. Since the compositions of f and g are the same, it factors uniquely through the small e. Therefore, alpha equals beta. We're done.
No, maybe you need to write something.
Okay, yeah, I guess what I need to write here actually is this, that I need to explain this square. I mean, this is, the vertical equalities are clear, and by definition, f composed with e equals g composed with e. Therefore, we have the horizontal equalities. And by definition of the equalizer, if it exists, if such factorization exists, it's unique. And it's unique. Is that clear? Okay.
So the next question is to show and pull back. Mono is mono.
Okay, again, let's draw a diagram. And let we have some object z and two morphisms, alpha and beta. Wait. Beta, what beta? And two morphisms such that composition of P1 and alpha is equal to composition of P1 and beta, and we know that G is monomorphism. Then we have, from this we obtain that this composition is equal и
Нет, там же есть вот эти
это, да, нужно вот сейчас две стрелки построить. And because this diagram commute, we can also write that.
Вы получили ответ на свой вопрос? Что вот эта стрелка, она единственная. Если бы у вас вот здесь еще было две стрелки, такие, что квадратик коммутативный, тогда да, иначе ничего не знаю.
Because of the commutativity from this we obtain this equality, and because G is monomorphism, we know that and now we have these two arrows to use the universal property, and alpha is equal to beta.
Well, maybe it would be better if you just draw these arrows and write on the diagram what are those arrows.
We can use here like the arrow, for example, beta равно альфа.
Please, can you explain? I can catch. What does mono of pullback means? We have two maps. Which one should be?
We know that G is monomorphism, and we want to prove that P1 is monomorphism. And symmetrically for F and P2.
Okay, for this case, okay. Thank you.
So now we go to the next question, which is to show that the map from X to Y is a monomorphism if and only if the following square is a pullback square. I think in this situation, terminology Cartesian square would be useful.
following problem. I'm not sure that we have time for this problem. Suppose you have a category with finite limits and inverse limits. Then show that this category has all products.
Products, not limits.
Products. You have a category with finite limits and inverse limits. Show that the category has all products.
Okay, so let's redraw this diagram so we have some space for additional arrows. So we have x, id, x again, id, and here we go to y by f. So let's first prove the direction that if we have have this as a terminal object, so if this is a pullback square, then f is a monomorphism, I guess. Okay, so suppose we have some other object z, and we have two maps from z to x. Yeah, okay. Like, 1 second. Yeah, okay, so we have to prove that if we have, let's draw this, a copy of the part of this diagram here. If we have two maps like alpha and beta from z to x, such that after composition with f they become equal, then we have to prove that alpha and beta are equal. But okay, let's then draw the map alpha here, the map beta here, and we see that the square is now commutative, exactly because the property that the composition with f equalizes alpha and beta. So this is a cone over our diagram, and by terminality of this object, we obtain a unique map. Let's call it, I don't know, let's call it H. But we immediately see that since this triangle, for example, is commutative, we have H equal beta, because here we have just ID. And similarly, we have H equal alpha because here we have ID. Okay, so this proves.
Maybe you write this H is equal to beta, H is equal to alpha.
Yeah, okay. This bounded triangle implies that H equals beta, and I don't know. Let's draw this. This implies H equals alpha. Okay, so this proves the implication in one direction. Sorry? We want to prove that f is mono. So we take two maps, alpha and beta, such that this diagram commutes. So alpha f equals beta f. Okay. Let's now prove the other direction.
We can pause for a second.
Okay.
Questions about the proof in this direction? Okay.
Yeah, so let's erase this mess. Now again, we have x, y, f. This time we know that f is mono, and we want to show that this is a terminal object. This is actually simple. Suppose we have again two maps, alpha and beta, and yeah, okay. we know that if we have a cone over this map, so, suppose we have a cone over this diagram. It means we have an object Z equipped with two maps, let's call them, alpha and beta. If this is a cone, this means that compositions alpha f and beta f are equal. But since f is mono, this means exactly that alpha equals beta. This time because f is mono, this implies alpha equals beta. So we have that these maps are equal, and therefore we can draw a unique arrow to this x, which is just alpha or beta, whatever you want to call it. So this proves terminality of this object.
Okay, questions? Actually, I want to go a little bit back when we discussed there was one question I wanted to ask you, but completely forgot it. This was the question about the products. Yeah, so the question about the products is the following.
So maybe I can erase this and ask the next question. So our canonical projections pi1 and pi2 epimorphisms.
Product with an empty set. Yeah. Do you want to explain this? No, I think it's fine.
So now that if you get your sets, epimorphisms are just. What I want to say is that in the category of sets, epimorphisms are the same as surjections. And we always have in the category of sets, because they are the usual product of sets, have this equality. So the projection then would just be the unique empty map from the empty set to our set, which is not surjective whenever x is an empty. So that's it. That's an example when this projection is not an epimorphism.
But it's still important to notice this property in general, that if you just focus on product in a category, you can assume this epimorphism. Yeah, so next question.
So let's try to understand the following property, kind of transitivity, if you want to call this, of pullbacks. So I'm just going to write the formula, but probably for the proof you need the corresponding commutative diagrams. So you take a pullback of fiber product over y with another fiber product over z. And maybe the right name for this will be some constellation property. Show that this is isomorphic to just fiber product of the x and w over c.
So so we have A from this one to Y. So the composition R1 and F.
Maybe you can write that A is composition.
Ah, okay. I can just write the composition. So we have one and only one morphism from this to this, because this is a pullback, these two elements. Yeah. This one will be A. So we have one morphism from this one to this one, because this is a pullback from this. And we have a lot of arrows. So we have this is so we have an arrow from this to this, because this is a pullback of X and W. So see. So we need to check that One minute. So что-то пошло не так. Сейчас. Да, окей. Уже? Сейчас. Окей. Вроде все было хорошо.